So hello everyone, welcome back to Algo Daily. In this particular video, we are discussing weekly contest 432, problem number C, minimize the maximum edge weight of graph. So in this problem, we have to look their example test cases and their code and their time and space complexity and dry run their example test cases. So in this problem, we have to given a two integer n and threshold, and we have also given a directed weighted graph of n nodes and the node numbered of 0 to n minus 1. Okay, and the graph is represented by the 2D integer array edges, and these edges are containing ai, bi, and wi, and which indicates their ongoing edges or ai node to bi, and ongoing and outgoing edges to ai to bi, and their weights we have to given. So now let's discuss their problem statement, then we have to jump their example test cases. So first we have to given a n and their threshold. Okay, so this problem statement simplify basically the we have to given a directed weighted graph, and this weighted graph with n nodes and labeled from 0 to n minus 1. Okay, and this is our graph representation of 0 to n minus 1, and after this we have to given a list of edges which represented as a edge of I is equal to, we have given ai, bi, and wi. This ai is our starting node, and this is our ending node. Okay, and this wi is our weight. Okay, and so we have their starting node, ending node, and their weights. Okay, and after this we have to given an integer of threshold. It basically specifying the maximum number of outgoing edges any node can have in the final graph. Okay, so this threshold work is to specifying the maximum number of outgoing edges. So our goal is, so now let's discuss our goal. So our goal is basically to remove some edges, these edges such as which node is 0, node 0 is reachable from all other nodes, and this is our first goal. And second, we have the maximum edges weight in the graph is minimized. And third, we have here each node has at most threshold outgoing edges. So these are our three conditions and three goals we have to achieve, and after we have to returning their answer. And if these goals are impossible, this is impossible, so then directly we have to return -1. So now visualize their test cases, and after that we have to implement their code. And so first we have here, so now let's discuss their example test case. So first we have given n is equal to 5, here threshold is equal to 2, and these are our edges, starting node, ending node, and their weights we have to give. And this is our initial point, and also this is our ongoing edge from 1 to 0, and their weight is 1, and same thing for all these conditions which all have to performing here. And now uh, first we have to visualize their values, like, one second. First, 1 to 0, this 1 to 0, this 1 to 0, our weight is equal to 1. Okay, and same thing for 2 to 0, our weight is equal to 2. 2 to 0, our weight is equal to 2. And next we have here 3 to 0, 3 to 0, and our weight is equal to 1. And 4 to 3, okay, 4 to 3, we have our weight is equal to 1. And same thing for 2 to 1 second, 2 to 1, one thing, 2 to 1, our weight is equal to 1. So these are our connections which we have to establish in this case. So first we have to remove edges to minimize the maximum weight while maintaining reachability to node 0. Okay, so first we have to minimize. Okay, so now we have to remove the edge. Okay, we have to minimize their weight which have the maximum weight, and then we have to minimize that. And first we have to remove the edge from 2 to 0. 2 to 0, their weight is equal to 2. Weight is equal to 2. Now we have here, after minimizing this, we have our another graph we have to here. Okay, the another graph representation is 1 to 0, we have another weight is equal to 1. And 3 to 0, we have here weight is equal to 1. And same thing for 4 to 3, 4 to 3 is our weight is equal to 1. And last is 2 to 1, weight is equal to 1. So now all these weights are getting here, and after minimizing this is minimized. And so now this is our graph. So this is containing this, and this one. Okay, this node we have to minimize. And now second step, what is our second step? Second step is, now we have to validate these reachability and their threshold values. Okay, so now all nodes can reach 0 through the path. Okay, so now we have to find this, and all nodes can reach 0 through the path. Okay, so so here we have this one. Okay, one second. So this one, 4 to 3, this 4 to 3, and then 0, this is one path. Okay, and this 3 to 0 is another path. Okay, and 2 1 0, 2 1 and 0, this is one path. And 1 and 0 is another path. Okay, so 1 and 0 is another path. So now we have to get here, each node has less than is equal to 2 outgoing edges. Now their threshold is equal to 2. We have to given here. Now the maximum edge weight in the resulting graph is equal to 1. So I hope you understand, because of this 4 is also connected with 3 and then 0 for this path. Okay, so this path, and now this 2 1 and 0 is also connected with this path, and this one is also connected, and this one is also connected. Okay, so the maximum weight we have to calculate it here is minus, sorry, 1. Okay, so now let's discuss their example, second two example second test case, so you have to better understanding of this. Okay, so now let's discuss this. So first we have here n is equal to 5, and these are our edges, and this is our threshold value. Okay, and so now we have to calculate their first we have to analyze their weight and their uh, values to ongoing edges. Okay, 0 to 1, 0 to 1 we have their weight is equal to 1, and same thing for 0 to 2, their weight is equal to 2, and 0 to 3 the weight is equal to 1, and 0 to 4 we have our weight is equal to 1, and 1 to 2 we have their weight is equal to 1, and same thing for 1 to 4 their weight is equal to also be 1. And now after this we have their threshold condition. So node, so threshold condition, so their node 0 to 4, this node 0 to 4, node 0 to 4, this outgoing edge which violate the threshold condition, threshold is equal to 1, threshold is equal to 1, and we must remove this condition to satisfy. Like whenever we have to create their graph, this 0 condition, this 0 to 1, 1 to 0, and same thing for all these condition. Like you can build a graph, and after analyzing these two we have to this one also be removed on that condition. So you can analyze with build a graph, and after remove this node you have to find their values. Okay, and after this we have their reachability, we have to find reachability. So reachability, how we can find, if we remove edges to meet the threshold value for 0, and some nodes cannot be reached into our init position. Init position, what is our init position? Init position is basically in this case is 0. We have to starting from 0 condition, and if it is not satisfied, then we have directly written -1. Also we have to we have also saying on here like -1 we have to directly return. So that's why this answer is -1. Answer is -1 because it is impossible to reach 0 from node 2. 0 from node 2 is not reachable, like not reachable. So that's why because of this weight is 2, and after minimize this we have to remove this one. So that's why we have here answer is equal to -1. So I hope you understand the logic behind that code and their implementation part, and so implement after this, sorry. And so now let's discuss their constraint for understanding. So here, so now we have here 2 less than is equal to n less than is equal to 10 to the power 5. This is a large graph we have to calculate here, and this is our threshold value. At least one outgoing edge per node it is allowed here. Okay, at least one node, and this one is our sparse graph, uh, sparse graph sparse graph condition. And after this we have there in this case, one second, this, yeah, no self loop will be using this condition a of I not is equal to p of I. Okay, and this is our 1 less than is equal to weight of I less than is equal to 10 to the power 6. It means edge weight can be large. Okay, and the key solution we use here, we use binary search to find their mid value. Okay, mid value. After mid value we have to calculate their previous and their next values, and after these we have a queue, and in queue we have to analyze their values. Okay, analyze their values, and like let's suppose this, which L is equal to 1 and R is equal to 2, let's suppose. Okay, of let's suppose we have to calculate their first example. Okay, try run their first example with binary search, this one. Okay, this one. This ARR of first we have 0 is equal to empty, let this one, and this ARR of 1 is equal to 0 comma 1. Okay, and this ARR of 2 is equal to 0 comma 2, 0 comma 2, and 1 comma 0 comma 2 and 1 comma 1, and after this one. Okay, and this ARR of this 0 is init position. Okay, and this ARR of 3 is equal to we have to get in here 0 comma 1, and this last ARR of 4 is equal to 3 comma 1. Okay, so this is our conditions which we have to performing here. So now after binary search, after binary search, let's set the value of L is equal to 1 and R is equal to 2, and after this we have to maximum weight of these edges to calculate. Okay, and their threshold value is also be 2, threshold value is equal to also 2. And now first binary search iteration, let's suppose the mid value is equal to 1, and after this we have to performing BFS. Okay, BFS, and their first node is 0. Okay, this is our init position, and BFS value is 0 in first case, and after visited nodes, their first value is 0. Okay, and Q is equal to also be 0. And now this is the condition: the node of 0 cannot reach any node with weight less than is equal to 1. So that's why the result is equal to false. I hope you understand the logic of this one. So how we calculate their so first we have to visited node is init position, and the queue position is init position, and after we have to checking with their conditions. Okay, so now let's discuss their second one. Like let's suppose in this case mid is equal to 2, mid is equal to 2, and start node is 0 and visited node. Now let's calculate visited nodes like 0, 1, 2 and 3 and 4, and the queue is also be same. Okay, here is same means this one. Okay, and the node value, node 0 can reach all nodes with weight of less than is equal to 2 because of our threshold value. And now this this will reach, then this will be true the condition, and after this we have to calculating these conditions like node 0 is reachable from all nodes, and to checking with all four conditions. Okay, all three conditions, sorry. Okay, all three conditions, this one and this one and this one. Okay, so I hope you understand the logic how we can check with their binary search and with their queue. And so it will a little bit tricky for you in first time, and but this will be a good question for how we can approach with binary search BFS, binary search plus BFS. Okay, and now let's discuss their let's discuss their code implementation part for better understanding. So one second. So now, so first we have their vector of ARR of n to initialize with their positions and their values. And now the purpose of initialization of ARR is a variable that store their result and their maximum weight encountered. Okay, in this case. So after this ARR is our adjacency list of u comma weight, and for all pairs this is incoming edges. Okay, and this ARR condition is O of n plus edges dot size. This is their time complexity of this code. And after this we have this one. Okay, so this one. Okay, so this one is now let this purpose is to of this code we have to populate the ARR of adjacency list using the input. Okay, and after this we have their u, v and w. This u is init, and this starting node, ending node, and their weight. Okay, w is our weight, and this ARR of v dot u. Okay, u comma w we have to initialize with, and after this we have to maximum their sorry we have to update result to store maximum edge weight. Okay, so this condition is performing this one key update result value and store their maximum edges. Okay, and now this auto condition and this lambda function is performing what, this lambda function recur this recur is to check whether all nodes are reachable from node 0 using edges with weight less than is equal to mid. Okay, so this condition to check with their edges with their weight less than is equal to mid, and now this visited is to track their visited nodes. We cannot track with again and again with unnecessary computation, so that's why we had to declare with visited. And this queue is a BFS traversal with initial value is 0. And okay, and after this we have their count to track the number of nodes reachable from node 0. Okay, and after this is our condition like this one. Okay, this while condition and the whole code, and this one is purpose of this is a BFS traversal. Okay, this one is for every edge is f2 v from their like node v is unvisited, and the weight of their edge w is less than is equal to mid. Okay, this one, and after this we have to returning their values, and this is simply a BFS condition for checking with their ongoing edges. And after this we have to performing all the operation like we have to calculate with their front value, and after front value we have to calculate with BFS all time when we have their another nodes. Okay, so after this we have there this one. Okay, so this one is basically L is equal to 1 and this rest this L is our range. Okay, range to find
smallest possible. Okay, smallest possible
Okay. And after this we have to calculate with their recur. Okay, we have to call their recur, and to return true all nodes are reachable using edges and with their weights. Okay, edges with weights. Okay, and after this we have to update their mid value, and to find their r plus r is equal to mid minus 1 and L is equal to mid plus 1 form. Okay, so this is their binary search, simple binary search iteration on this behalf. Okay, and after the smallest maximum edges weight, then we have to return their answer. So now let's discuss their time complexity. Okay, I hope by the way, I hope you understand the logic of this code and their implementation part. And so first we have their build their adjacency list. Okay, build their adjacency list. This will be edges dot size, and second one we have calculate with binary search with range of the binary search range of 1 comma their result. Okay, so the value of this one is log result. Okay, for iterations. And after this the BFS, we have to calculate BFS of lambda expression. Lambda expression, the time complexity of this code is n plus lambda expression time complexity, n plus edges dot size. Okay, so the total time complexity of this code is, we have here O of edges dot size. Okay, edges dot size plus 1 plus this one plus this one, and this is our time complexity, log result and n plus edges dot size. And same thing for, we have to calculate their space complexity, and the space complexity of this code is, first we have to create a adjacency list of n plus edge dot size edges dot size, and we have to create a visited array, and one we have to create a queue with n. Okay, so that this is our total space complexity, and the total space complexity of this code is O of n plus edges dot size. So now I hope you understand the logic and their implementation part. And so thank you everyone, thank you.